of you who can make it. And if you couldn't make it because of the snow, that's totally fine. You can watch so on Zoom later. In case you didn't get the message, we're not having the quiz number 3 today, being there are only about 15 people in the classroom. That's probably a good idea. We'll have it on Monday next week. So today we'll cover how to extend linear regression to higher dimensions and how to do polynomial regression. We'll see these are kind of roughly doing I'm doing the same trick. Once you understand kind of the first part, the polynomial part with one additional trick will be pretty easy. So let me quickly look at the schedule. Again, I moved quiz number 3 to Monday, so we'll do a full lecture today, and then we'll do quiz 3. It'll cover the exact same materials planning. We already made the quiz, had it printed, kind of ready to go. We'll just give the same quiz on Monday. So it'll cover this lecture and the previous 2 lectures. So it was a short kind of week because of President's Day. So let's see. The other thing to note is homework 3 was posted. Homework 3 will be on regression, the current section we're doing. And so you will I expect you pretty much do most of it in Colab. There's still, like I posted a draft of it on Overly if you can write up in there. But a lot of it is just kind of working through an example based on a data set, a one-dimensional X data set, and a one-dimensional or Y data set. And you'll build linear regression on this, and you'll kind of walk through all the things we'll do through this class, and the next one with cross-validation will be kind of focusing on what the second question is about, and then polynomial regression, what the third section is about. So it looks like a lot of small pieces, but each step should be pretty quick, I assume. So kind of just practice to force you to kind of walk through all the things we'll be doing. So well, that's posted. You could probably get started on it, especially after this lecture, and some stuff with cross-validation we'll see next week on Monday. It's great. So any questions on this? All right, so let's get into the lecture. We'll come back. We'll do a few examples in Colab today as well. So we'll see how to implement a few of these things. Okay. So today we'll be talking about where the input to our regression problem is going to be this uppercase XY, and now we're going to be modeling the uppercase X as a data set in RD and its corresponding kind of labels in which are these real values, right? So I can write this uppercase XY now as this set of these pairs, X1, Y1, X2, Y2, up to Xn, Yn. And so now the difference is that each of these Xi's is going to be a vector in RD. We're still going to have that the Yi's are going to be these real values. Okay, so the Yi's are still scalar values. There's still one value we're trying to predict, but so these are the dependent. So these guys are the dependent value we're trying to predict. It's easy when this is just a single value that we're trying to predict. And we're also going to have the explanatory variables. right? The explanatory variables, which are we're going to build our explanation from. Okay, it's not necessarily going to give us like a causal sort of relation from X to Y. We kind of maybe intuitively might think of it that way, but I don't want to make any claims about that. We're just trying to find some patterns of association here. Okay, and so the notation gets a little bit dense here. Each xi, right, is a vector in Rd. So this is kind of an xi1, xi2, xi3 up to xid, right? So now I have two subscripts here. So it's a little confusing. I'll try and avoid writing all this out. Sometimes I'll just refer to a single vector x and then do just the subscripts on that, dropping the I. All right, so it'll be a little messy to write out some of this stuff now because we have really a matrix of data, but hopefully we'll be able to kind of be able to cut through this and see what kind of the simple way of representing these models are. Okay, and now our goal, right, is to, so this is our input, the goal, okay, is going to be to try and predict these yi's using some model of the xi. I want to build a model so I can input the xi, which is now a multi-dimensional thing. It's a vector of values of a bunch of attributes, and I can try and predict what this y. This yi hat should probably be close to these yi's. Okay, and okay, so we can draw a picture like this, like we did before, where y is these real values we're trying to predict, but now instead of one dimension, you could think of, you have this d-dimensional space down here. And so now I've got a data point xi, which is a multi-dimensional vector. And then there's some sort of function, right? And this function is really this kind of this, right? It's going to be a plane. I'm going to do just linear regression here, right? So it's really this plane here, where for this observation, this data point, I lift it up and it will intersect this plane in exactly one spot. And this will correspond with a value. This will give me my prediction, yi hat, right? So I still have a function, but the function, instead of going from a one-dimensional space, is now going from a d-dimensional space, right? So for every observation, every d coordinates, there's exactly one kind of, I draw the line up and it's going to hit the function in exactly one spot. That spot, that height of that spot, how far up I go, is going to give me the y value, which is my prediction. Okay, and so we're going to do still these linear functions, and these linear functions are going to work kind of very similar to the linear regression we saw, where x was only one dimension. So if we keep that the model has to be linear, everything is still going to be simple here. Okay, so before we had that, we could describe the line of the model from x to y as an offset, and then the slope of the line. Now it can be so more complicated, but not that much more complicated. We're going to have an offset. We're going to call this offset is going to be alpha 0 instead of b. And then we're going to have a term for each of the coordinates. Okay, so we're going to have j equals 1 up to d. These are the d coordinates of my xi, right? And so for each xij, I'm going to have a corresponding alpha j. Okay, so now this will be parameterized by some alpha. Okay, my alpha is going to be alpha 0, alpha 1 up to alpha d. So this will be a d plus 1 dimensional vector here. And these will be the parameters of my model. And it's always, if it's a linear function, it will always have this form. I could also write this out as alpha 0 plus alpha 1 xi1 plus alpha 2 xi2 plus ... alpha d xid. Right? So it's because we're only looking at these linear functions, it has to be linear in terms of all the input values, which are the xi's, right? The xi1 through xid, those are the only observations we have. It's a linear, if it's a linear function of those, it has to be of this form. Okay, and we can actually write this more compactly. First of all, we can imagine that there's a 1 here, right? So this, so this 1, I can always put a 1 in front of this, this alpha 0 here. And then it's a sum. It's a sum over terms where I'm multiplying an alpha value by its corresponding xij value, right? And so this means that this can be written exactly as a dot product. Alpha 1 xi here, right? So this 1, I can kind of, my alpha was a d plus 1 dimensional vector, and my xi was a d dimensional vector. Okay, so they weren't the same dimension, so I couldn't take a dot product before, but I always had this offset term as well. And so I can just pretend like there's a 1 here, and fold this into the first term in this x vector, and now they're both d plus 1 dimensional vectors. Right, so this is equal to alpha dot with the dot product with 1 xi1 xi2 ... xid. Right, so I can write this as a dot product. Okay, so the model for linear regression with multiple kind of multiple dimensions in the explanatory variable or variables is just going to be a dot product. All linear functions are just these dot products. That's all they can be. If it is a linear function, I could write other kind of linear functions, but I can always simplify it into this form. All right, so we're using just this dot product again. Okay, so what we're gonna do instead to try and solve this function, this green function that kind of is modeling these data points, which are now multi-dimensional, with their one scalar value label that we're trying to predict. We're gonna have to solve for these alpha values. Alpha is now a d plus 1 dimensional vector. So instead of solving for this a, the slope, and b, the offset, we're now solving for d plus 1 values. So at once, turns out the algorithm for solving is not going to be too much more complicated. We'll be write it down in basically closed form, but it's so okay. We should move classes online if you start after now. Okay, so we started already. All right. So we will see how to solve for this alpha. It's not going to be too bad. Roughly closed form if you're willing to do a little bit of linear algebra. All right, so let's look at a simple example before we go any further. This is, so I'm going to pretend this is data from a website, okay? And so what websites try and do, they want to try and turn people go to their, if they're selling products on their website, they'd like you to buy some stuff, right? And so when you come on the website, they track your movements on the website. If you're on your computer, this is an old example from when people used their mouse on their computer instead of their phones, but kind of a similar sort of thing happens where you spend a certain amount of time, maybe in seconds, on the website. You jiggle the mouse by a certain amount while you're on there. The more you move the mouse, probably the more likely you're engaged with it. And the more you scroll down the page, right? Scrolling works on your phone as well. So maybe the amount of times you move your finger on your phone, the amount of time you spent on there, the amount you scrolled. And this is, for these customers, how much they spent in cents on the website. So this was pretty successful. They monetized, almost all the customers except two actually bought some. So they'd like to build a prediction. So if I get some new, data, a new customer, I'd like to predict how much they will spend on the website if they're spending more time, more jiggling of the mouse, more scrolling, and how this corresponds to prediction if like how much I would expect them to buy. Okay, so this would be kind of a scenario. I'd like it's some function of these three different these measurements you can make. Okay, these are not so different from what websites actually try and do and track. It might be more discrete, and there's various other ways they do this, but this is the sort of kind of for predictions they actually do. Okay, and we're going to, so in order to turn this to a problem we can solve with regression, with multiple regression, we want to model these as these variables. Okay, so we want that we think of each row here as one of these data points. Okay, in particular, this part here, just these coordinates is going to be x1, the first row, the first data point. The second one is going to be x2, and this one over here is the corresponding, so y2, right? So we want to predict what the sales is going to be versus these three variables over here. All right, so I'd like to turn this into a problem I can solve. So I will be kind of gathering this data. We're going to transform it into a matrix. Okay, and so I can also think of the rows of the matrix, right? So this will be the first row of the matrix. Call this uppercase x1. This will be uppercase x2. Uppercase x3 would be this would be the column of the matrix. Sorry, I think it said row before. Okay, and I'd like to kind of turn this into a big matrix X of all of the explanatory variables. But I want to also make sure I am able to model the offset. So I want the matrix to be bigger, so I'm going to add a 1 to every one of these data points. Okay, so I can say that there's a 1 in front so that I can solve for the offset all at once using just just linear algebra. And so our data might be X and Y, right? And X is going to be equal to X1, X2, X3, but I'm going to turn this into what I'll call X tilde instead. And X tilde is going to be this all ones column, then X1, then X2, then X3, right? So I'm going to treat this column in front here as another variable. So instead of a three-dimensional data set where I have to model the offset separately, I'll treat it as a four-dimensional data set where I no longer have to model the offset. Okay, so I'll be able to turn this into X tilde, which will be an RD plus 1. Okay, so I'm going to work with this matrix instead. And I'd like to predict now an alpha in RD plus 1. Oh, so this was in, sorry, X is not in RD plus 1, right? This is, X is in N, X is in N cross D plus 1. Right, because it's going to have N rows. How many rows do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 11 rows in D plus 1, which is 4 of these columns here. Okay, I've added this one in front, and I want this alpha. I want to find this alpha so that for each, so if I get a new, so the goal now is that if I have a new X1 equals, let's say 500, X2, that's the amount of time and seconds they spent on, the amount of jiggle is 30, and the amount of scrolling, let's say is 50, then I can build a model here of this X1, X2, X3, which is going to be alpha 0 plus 500 times alpha 1 plus 30 alpha 2 plus 50 alpha 3, right? So this model will give me a prediction of how much money they'll spend on this side. I'd like to solve for those alphas. So when I get this new thing, I can predict, and then I can say, okay, if I can get them maybe to spend more time scrolling, then they're more likely to find another product they like and click on and see which of those variables is more important here. All right, okay, this kind of makes sense, the goal. We'd like to find a function that takes into account these three things and see how jointly important are they for predicting this Y value, the amount of money customers are going to spend on the website. Okay, and it's going to take this form of the linear equation. Okay, so again, our input now is going to be an X n by D and Y in Rn. And instead of just saying we'd like to, what the model will look like, to write down the goal, we're going to write down a cost function. And it's going to be the sum of squared errors again, times some model that's parameterized by alpha. And we're going to call this, yeah, and so, okay, and the sum of squared errors is me I of 1 to n of the yi minus the prediction of the model at xi squared. Right, so this is, again, it's the value we observe minus the prediction, that quantity squared, right? And so if we have, right, this picture here where we have this RD, these are the Y values, And so there's going to be some model here, which is this linear kind of function here. So we actually have a point, we'll call this xi, yi, which you could look at the xi value, but if I were to actually map this up here, it's actually going to give me a height instead. If this is the yi observed, okay, instead I'm going to get this yi hat instead here. Right, so this difference between these two, this difference is going to be the residual still. Okay, so I'm still going to get a residual error where I'm mapping from this xi value, and I observe it here. It's in this multi-dimensional space, but it has a height yi, which is what I observed. But the model, if I map it up to where it intersects this green plane through here, it's off, and this gap between them is going to be the residual. So I still can have this residual only in the y direction. Okay, it's only the difference in the y coordinate. And so that means that this sum of squared errors is still going to be the sum of the residuals squared. Right, so I'm going to measure this difference in the y value and just look at this residual squared is what I would like to minimize. Okay. And so again, the input is the x and the y. The alpha is what is going to determine this green function here. Right? This alpha term here is what's going to determine the green function. So it might be useful to write this out instead, explicitly saying what this alpha is. It is, so I can write this as I equals 1 up to n of this yi minus alpha, the dot product with 1 comma xi, this difference squared. Okay, so now I can see this alpha here is inside this linear function, and the goal is to choose the alpha to minimize this, right? So I can maybe call this a function of alpha, right? So now there's a function of alpha that's determined. What the function is that I'm trying to minimize is determined by the x and the y values. Those are my input. Those describe this function, and now we need to find the alpha, which makes this as small as possible. For different, now alpha is a vector of a d plus 1 dimensional vector. I have d plus 1 values. I have to minimize all these at once, right? So the alpha star is going to be the arg min r d plus 1. I want to choose the alpha that minimizes this sum of squared errors of x, y, m alpha. And if you write it here, it looks like it's focusing on the wrong terms. So we can write this as arg min alpha in r d plus 1 of s of alpha, right? So there's this function s of alpha, and I want to solve for alpha that's minimizing this. It's now a vector. We kind of looked at this when we were only computing the mean in 1 dimensions. We could think of this as a nice convex function, and the minimum we could find by taking the derivative and finding where the derivative was equal to 0. Okay, we're kind of going to be able to do the same thing here, but it involves linear algebra instead, and I don't think I'm going to go through the proof. okay? But the solution here is going to have a nice form. Okay, it's going to be this x tilde transpose x tilde inverse x tilde transpose y. Okay. Okay. Let me highlight this because this is very important. You kind of, so that it's looks kind of complicated, but it's not so bad. You should probably will like eventually memorize this. But like I had an algorithm before for the case when x was one dimensions, this is our algorithm now when x is multidimensional. In fact, this works in the one dimension case. I can turn the x into the x tilde. Remember, the x tilde is the one where I added the one in front. I instead of index from 1 up to d, now I start my index at 0, and the index 0 is always going to be a 1. So I turn this into a vector. I turn each data point into a d plus one dimensional vector. I stack these into these matrices, these x tilde. Okay, x tilde is now an n by d plus one dimensional matrix. Okay, and y is an n dimensional vector. And now I can apply this linear algebra operation. I do x tilde transpose times x tilde. I do an inverse on this. Okay, and I multiply this again by x tilde transpose and by y, and this gives me the optimal answer. It's effectively a closed form up to how to take the inverse. Okay, I haven't explained how to compute the inverse yet, but if you believe that we can compute that using Python or whatever, then we can directly compute the optimal answer here. This is, again, kind of a direct algorithm to compute the optimal least squares regression for multiple coefficients at once. Okay, so pretty cool. We have this nice algorithm here, right? So this is our algorithm that we can call. Okay. All right, let's go through this a little bit more carefully just to make sure all the steps are clear for multilinear regression. Okay, so 0, the input is going to be x, y in our n by d cross r n. Okay, 1, I'm going to convert x to x tilde, which is going to be an n by d plus 1. So x tilde equals 1, 1, 1, 1, 1, and then it's going to have x here. Okay, so I'm going to add a column in front. The 0th column is going to be all ones. Okay, so it's going to be an all ones column. This is an all ones column. Okay, so now I have this x tilde. Okay, so now I can, the tricky part here is I'm going to do x tilde transpose times x tilde. This will now be in, what's the dimension of this matrix going to be? X tilde was n by d plus 1. So what's x tilde transpose times x tilde? What's the dimension of that going to be? What? 3 by 4 in terms of d. So it's not going to involve n. So x tilde transpose is going to be d plus 1 times n. right? So I have a D plus 1. This is D plus 1 times n. This is n by D plus 1. The n's are going to cancel out. So this matrix is going to be D plus 1 cross D plus 1. Okay, so typically D is going to be much smaller than n in a lot of the cases we'll think of in this class. And so it's not too big of a matrix. Okay, so this is not going to be too big. In the case before, when we had this example here, D plus 1 is going to be equal to 4. Right? So this will be a 4 by 4 matrix. Okay, and so the next step we're going to have to do is we're going to have to invert this. Right? X tilde transpose X tilde inverse. And I can only do this, okay, it's only invertible if this, well, let's call this M. No, we used M for something else. What should we call this? Let's call this Z. If Z is it's a square matrix. We can only invert a matrix if it's square. It's square, it's D plus 1 by D plus 1, okay? When I multiply something by its own transpose, I make it into a square matrix. And it has to be full rank. Okay? Is this going to be a full rank matrix? Okay, I can only invert it. I can only invert if it's going to be full rank. Is this typically going to be full rank? So I started with X tilde or X as an n by D matrix, right? And I've increased the rank by 1 by going to X tilde, or I've increased the dimension by 1 to X tilde. But usually, like in this example, n was like 11 and D plus 1 was 4, right? So n was bigger than D plus 1. Typically, this will be the case. Okay, so we'll be in the regime where n is often going to be much bigger. And so it would be rare for it not to be full rank. That would have to be if a lot of the rows were linear combinations of like almost all the other rows. So if I have D plus 1 rows, which are linearly independent of each other, then it's going to be, then this square matrix will be full rank. Okay, if X tilde is full rank, then X tilde transpose times X tilde is also going to be full rank. So unless I have very degenerate input, this will be full rank and this step will be okay. Okay, so this is usually fine. So this is usually good if n is much bigger than D. Okay, so if n is sufficiently bigger than D, then this should be safe to do. So then I can do this transpose. Then I can do this inverse. So and the inverse of it is also going to be a square D plus 1 by D plus 1 matrix, right? Okay. And then the fourth step is alpha star is just going to be X tilde transpose X tilde inverse, which I'd pre-computed from above, times X tilde transpose times Y. Okay, and this is just matrix multiplication, right? So I can multiply this through. Okay, so this is kind of the tricky step. You have to worry about doing this inverse, but in most cases it will be fine. We can do the inverse. Okay. Okay. The other thing to I think worth thinking about is let's look at this expression again. X tilde inverse, X tilde transpose Y. And I want to compare this to when D was equal to 1, then we had this property that A was equal to x dot y divided by the squared norm of x. And then we could also do this. This B was, then we can solve for the offset. So the B offset separately. Remember when D equals 1, I wrote down this other algorithm where we could solve for the slope in this way, where we took the dot product of x and y and we divided through by x by the norm of x squared. Okay. So I'm going to argue that this is pretty much the same kind of operation here. And in fact, this is basically the same thing, this dot product of x and y. Well, that's what's going on here. If I just had a one vector x to solve for one value of alpha, this A, I would just take one of the columns of x tilde, and this is the dot product. And so instead of dividing this x squared, that's pretty much what I'm doing here. I'm kind of squaring x times itself. I can multiply a matrix by itself when I do the transpose, so that allows me to multiply it by itself. I get some sort of kind of a squared norm of this here. And the part where I'm dividing is like the inverse, right? So by dividing by that, I'm kind of multiplying it times, or taking to the power -1 and multiplying it, right? I don't really know how to divide with matrices, but I can do an inverse. And the inverse is kind of allowing me to do this division. So it's kind of doing the same sort of operation here as we did in this B+1 case. Okay, but it's more complicated. It's solving for everything jointly. It's a global solution. It's solving for all the alpha values at once that optimize this expression, minimizing the sum of the squared residuals. All right, so this is a, so it's not solving each alpha I at a time. It's solving for all alpha I in this alpha globally all at once. Okay, so at the end of this, we're going to get out an expression. We're going to say yi hat. Our prediction is going to be alpha 0 plus alpha 1 xi1 plus alpha 2 xi2 plus ... alpha d xid. Okay, and so it's common to try and read into this expression and to say, if this value is, this coefficient is large, if this A1 coefficient is large, I might think, okay, this term, if large, then maybe this xi1 is important. Okay, maybe this term is important if this coefficient is large. This gets a lot of weight in this sort of prediction here. Okay, this is not necessarily true. It's not saying this term is necessarily more important than the other terms, but it's saying that this is part of the global best solution. It could have been, I can get almost as good of a solution by making this term as large, but this one was slightly better. They may be correlated with each other. And it's not really sussing out the correlation between these things. So we don't want to draw too much inference or prediction into the individual terms here. We want to think of this as a global solution and use it just as that. Okay. This is a very common kind of, people try and read too much into the importance of these coefficients. part of the reason we can't tell how important it is they're kind of canceling out the what the units are. We could have these different terms, right? Remember in our example when we had the amount of time on the website, the amount of jiggling it did, and the amount of scrolling it did. Those may have had different units that were describing different kind of different aspects of the interaction on the website. And the alphas are canceling out those units. So if we change time from second to be in minutes or milliseconds, that would change what the coefficient is. Okay, that's part of the reason. You can maybe try and normalize these terms first, but it doesn't totally tell you the individual importance of these terms. We should not read too much into this. Okay, so do not read too much into kind of something just a large coefficient here. All right, but it gives you a global expression that fits the data well. Okay. All right, what do I want to, okay, before I want to get to polynomial regression, but let me just show you how simple this will work. This was, again, linked off of the web page. I've read in this data from, I've kind of written in this expression. The NumPy array is now a two-dimensional array. Each row, this is the first row, is the first 4 values here, right? And I put a 1 in front of every one of them. I automatically added this 1 as example here. So this is actually x tilde. This for simplification, I just wrote x. And I printed them out in this column here. And I'm using NumPy again here. And y, it wrote out as a row vector because it likes to print them as row vectors. Okay, but I've written in this data, and now I want to solve for it. Here's my algorithm, right? I just do, I need to have this linear algebra inverse function, but I do x transpose dot, times x, inverse times x transpose times y. It gives me out the answer. I wrote a as a vector a instead of alpha, but it gives me out these four coefficients here. Okay, so I could write the linear algebra myself. Of course, they have it built in a variety of ways to do this, right? So I can call this linear algebra package least squares with I don't have a condition number on there that's over parameterized stuff, and it give me out the same numbers here, right? So our algorithm, which is this simple linear algebra, it's calling the same function as here in turn. It gives me out the same sort of coefficients. Okay, and let's just kind of check how well this works. I can pull out one of the data points. This is the third row, right? Index 2, but I start counting at 0. So this should be in the third row in the data matrix, x3. It gives me here, and I to evaluate it, how well my model works, it's going to be a dot product, right? The model is always the dot product. So to evaluate it, I just take my vector A and I dot it with x3. This gives me the prediction, the value. I predict they'll spend $81.93. Okay. How close did we get? This is y. The third value in y was $76.50. Okay, so it did pretty well. Okay. And I can try and read into these coefficients, like what does, maybe this means this is the offset one. This is the one that gets multiplied by 1. So that means they spend its times 1,000. So I guess they expect them to spend, or is that times 100? Forget. But okay, so forget the scientific notation. I hate when it writes it out like that, but okay, so we can But I don't want you to read too much into the actual coefficients. Think of it as a single modeling function that is trying to tie everything together, okay? And not to read too much into the individual coefficients you get out here. All right, so this makes sense. Pretty simple algorithm how to do this. Now you can apply this multiple kind of like still build a linear model, but from multiple random variables at once. Okay. All right. Okay. So the second thing I want to cover in this lecture, okay, is going to be polynomial regression. And so now we are going to be able to move beyond these linear models. We're going to have, right, this is going to be in R. And now we're going to assume that our x's are just one-dimensional again. Okay? So our input is going to be xy, but this is now going to be in R by R here, right? So this is going to be xi, yi, the set xi in R and yi in R. So you can apply this to multi-dimensional xi again. It just gets more sort of complicated. So let me explain how this works with one-dimensional x. And I think later on we'll come back and show at some point how to do this with multi-dimensional x. It's just lots of notation to work out here. But the thing I want to do now is instead of doing a linear function, I would like to build a non-linear function. So it still has to, for every xi, it has to map to exactly one value of yi hat, okay? But it doesn't have to be a linear function anymore. It can be a curvy function, okay? And so I will allow this curvy function to be defined by a polynomial, okay? And so we're going to write down where yi hat is going to be a model. And we're now going to say a polynomial model of degree p. Okay. And so a polynomial model will look like it'll have an offset. It'll have a linear term. And then it will have more terms here, x2, x squared here. Okay, so this would be if I set p equals to 2, this would be what a degree 2 polynomial function would look like of this kind of a scalar value x, right? So a degree 2 polynomial has an offset, potentially a linear term, and going to have a quadratic term. Okay, so this is p equals 2. In general, if I have a function that looks like this, it means that if I were to draw it, it has to look like a parabola. Okay? This is M2. It has to look like a parabola. I can only fit things that look like parabolas now. If I want to fit something that looks like the green curve, I have to be able to go up and down, have these inflection points. I need to have a higher degree polynomial, right? So if I want a higher degree polynomial, then I would say P of x is going to be alpha 0 plus alpha 1x plus alpha 2x squared plus alpha p x to the power p, right? Or in general, I can write alpha 0 plus j equals 1 up to p of alpha j x to the power p. Or I can just write this as sum of j equals 0 to the power p alpha j x to the p, because if I x to the power 0 is always going to be 1. If I take anything to the power 0, it's going to be 1. Okay. And this one is actually easy to see. It's, again, this dot product. Okay, so I can write this expression as a dot product. And I've taken, what I've done is I've taken my single value x, right, single scalar x, and instead of adding just the 1 in front of it to expand the dimension by 1, I've also taken it to each of the powers up to p to expand the dimension up to dimension p plus 1. Okay, so how I do this is, all right, so for polynomial regression, of so degree p, you take x, y, where x is an r, and you map it to, we'll also sometimes call this v, if this is xi, to vi, which is going to be 1 x squared up to xp in rp plus 1. Okay, so now, right, if I have a vector x, right, this was in Rn. I have n different values here. I'm a little off the screen. Rn, I've got n different values in it. I'm going to map this into one, 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 x1, x2, x3 up to xn, x1 squared, x2 squared, xn squared up to x1 to the p, x2 to the p, up to xn to the p. Right? And so this will now be an n cross p plus 1. And we will call this guy x tilde p. Okay, so instead of starting with a d-dimensional vector, I'll start with the one-dimensional vector. I'll expand it up to p dimensions by taking it to each of the pth power and still add the all ones column in front here. Okay. And so now I can still write my model p, which will be parameterized by alpha of x. I is going to be the dot product of alpha times this vi. The vi is going to be the expansion of x up to this p plus 1 dimensional vector. Right, this is alpha 1 xi squared up to xi to the power p. Okay, so I can very simple, kind of a very similar trick as I did with linear regression to get rid of the offset. I can also take this value and take it to every pth power, and I automatically get this kind of more complex. I can have this model be much more complex. Okay. So before I go through this again, let's look at this example, and we'll go through this in Colab in a bit. But I'm going to start with the same example we used for linear regression, where we had just one dimension, so height and the weight. And I plotted this before, and I'm going to add some more data here to try and build this out. Right, so I've added some more data points here, and these are plotting. This is, so you can, this is off the bottom here. I've missed one of the guys off the bottom, but okay. So I can still plot this by the height and the weight here. And what I would like to, instead of fitting this linear line, I'd rather try and fit a curve that goes through like this. So I'd like to get a model. And this model, like how complicated do you think, what degree of polynomial do you think this green model would have to be? What do you, can I do this with the degree 1 polynomial, p equals 1? P equals 1 is exactly the red line. That's what the red line will give me. P equals 2, can I get this model with p equals 2? No, p equals 2 has to be a parabola, right? And this is too complex for a parabola. Do you think it could fit it with p equals 3? Yeah, I could maybe do this with p equals 3, right? I can choose any polynomial of degree 3 here, and I can choose one that just goes through these data points just like this. So it can have one inflection point here. And it starts small and it ends large. This, okay, this seems like it could make sense. All right. So, so again, what I would like to do is I would like to look at the sum of the squared error, xy, of my m p alpha, which is again going to be the sum of yi minus mp alpha of xi squared, right? And this is still measuring these residuals, right? Okay, so if this is xi, yi, then I'm still looking, that's measuring to the red curve here. That was a bad example. Let me try again here. Okay, so let's look at all the residuals are smaller now. In fact, I can always get smaller residuals by fitting a more powerful curve. The more powerful function I have here, if this point is xi, yi, then this is still ri is going to be yi minus yi hat, right? And this is my residual. Okay, and if I have a larger family of functions, that green curve, if it's a degree 3 polynomial, it has an option to be the red curve, right? If I set coefficients alpha 2 and alpha 3 equals to 0, I will get the red curve. So it could do the red curve, but I'm going to find one that has a smaller fit of the residuals. Here, I want to minimize the sum of the squared residuals. So the more powerful I make my model, the smaller I can get in the residuals and fit the data better and better here, right? So my goal is to get an alpha kind of star, which is going to be the arg min of alpha in rp plus 1 of the SSE, sum of squared errors, okay, so I would like to minimize that choice of the models, and there'll always be the polynomial models of degree for some choice of p. Then I choose the alpha, which minimizes this the sum of the squared residuals. All right. So, okay, so hopefully now you can kind of see the algorithm of how to actually do this. Our input is xy in Rn cross Rn, our model MP alpha of x is going to be equal to the sum of j equals to 0 of p of alpha j x to the power j, right? And so our model is going to be alpha 0, alpha 1, up to alpha p. And I need to solve for this alpha. And then the goal is going to be a alpha star arg min alpha in rp plus 1. That's minimizing times this model p alpha xi squared. Okay, and so in order to solve this, hopefully the algorithm makes sense. We're going to create an xp tilde, which is this expansion 1, 1, 1, 1, x1, x2, up to xn, x1 squared, x2 squared, xn squared, up to x1 to the power p, x2 to the power p, xn to the power p, right? So I can think of, remember, this guy here was our v1, right, which is this vector in our p plus 1. Okay, and then I can solve for my alpha star. I can write this directly as the same linear algebra expression, xp tilde transpose xp tilde. This, I take the inverse xp tilde transpose y. Okay, so now I have my algorithm here, my linear algebra. After I do this expansion up to this n by p plus 1 dimensional matrix, I can just apply the same linear algebra as I did before, just like the multi sort of linear regression problem, and I get the optimal algorithm that will solve for the green curve that fits this data very well here. It's just like a multidimensional problem, right? So this is my algorithm. Okay. Okay, so I have a nice algorithm for polynomial regression here as well. Okay, just so it's a little bit clear, let's give an example. Let's say 2, 4, 3, and y is equal to 1, 6, 5. I just want to make clear, let's say p is equal to 5, and I want to write out xp tilde, right? What would this matrix be? Well, it's going to be, this should be in 3 by 6, right? It's going to have 3 rows and p plus 1, 6 columns. So the first column is going to be all ones. The second column is going to be 2, 4, 3, right? I'm just going to use the x, not the y. The third column will be 2 squared. That's 4. 4 squared, 16, and 3 squared, 9. Right? Then 2 to the third, 8. 4 to the third, 64. 3 cubed, 27. Right? 16, 256, 81, 32, 1024, 243. Okay, so this is my x tilde p. This is an example, just right. So this is what the expansion would look like. Then I put this as input to the multilinear regression problem, and I'll output this degree 5 polynomial. Actually, what would happen if I tried to do this? What if I did xp tilde transpose xp inverse? What conditions do I need for it to be able to take an inverse? Full rank and square. Is it going to be square? Yeah, so it'll be a 6x6 matrix. Great. What will the rank of this be? The rank will only be 3. Okay, if I take xp tilde itself is a 3x6 matrix, and it's only going to have rank. It's going to have, each row is going to be linearly independent of the other rows, but that means it's only rank 3. I multiply something by rank 3 by something else that's rank 3. The transpose doesn't change the rank. It can only be rank 3. So this square matrix, the 6x6 one, is not full rank. It'll be rank 3. So if I try and take the inverse, it's going to say, uh-oh, it's not going to work. Typically, you can do something called like a more Penrose inverse. It's like a pseudo inverse. And so depending on what function you call it might actually work still, might give you an answer if it's inside regression. But generally, you don't want to fit a degree 5 polynomial to only 3 data points. Okay. Yeah. All right, so let's see this working in Colab. Okay, let's see an example here. Okay, okay, so I'm going to plot some stuff. So I have NumPy, but I also have matplotlib. Okay, I'm going to define, this will be my plotting function. What is this going to do? I'm using my height and weight data. So it's going to go, this is similar to what I did before. I'm going to plot the data points from the x-axis from 60 to 76 and the y-axis from 100 to 24. That way, no matter what I change, they will always look the same way. Sometimes the curves are going to go outside the bound, and I want to make sure we can still see it. Okay, the lin space between 60 and 76, these are the heights I care about. 101 things I'll do, and I'll use this function called polyfit, which will fit a polynomial curve of degree p here. It'll give me the coefficients, and then it can fit. And this is just the machinery used, it's gonna plot them. Okay, so this will be my plotting function. Okay, now I've got my data. This is the data I showed before in the slide, and here's a degree 3 fit. Right, we can see if I can change this to a degree. I get my keyboard. Should have brought my. Okay, should we change this to degree 2? See what happens. So if I use a degree 2 fit, you're right, it doesn't quite work as well, right? It has to be a parabola, so it can't really go through the 2 bends here. If I do a degree 3 fit, then I get this nice curve that kind of is going with the bends in the data, right? Okay, and the residuals are getting smaller and smaller the larger I fit the degree. What other degree should I try here? 20. Let's not go up there quite so far yet. Let's make it up there. 5. I can see a little bit more expressiveness. There's some things that are kind of off, a few points that are, there's kind of a really dominant curve here, And then this one is going to be really hard to fit. It's going to be hard to fit both of those. Right. Let's go up to 10 first before we go up to 20. Let's see what happens. With 10, it's trying to somehow fit these other data points. It's doing a little bit better here and trying to do something here, but it's pretty tough. It's going through a lot of them exactly. Do you want me to go up to 20? Let's see. Should we do 18 first? Let's see what 18. With 18, it didn't quite fit all the data here. With 20, it's not fitting them either. All right, so why is it, you'd expect if there's 20, it would fit it exactly. Why is it not fitting it exactly? Or do you think it should fit it exactly? Yeah, it has a really sharp angle at the end there to go through that last data point exactly, but it's not able to fit these two here yet. Okay, it probably could with the degree 20 polynomial, but what Python is doing here is it's restricting, it's got this message here, polyfit may be poorly conditioned. Okay, so I've done this inverse matrix, and the inverse matrix, it said you've taken the inverse of something which is almost not full rank. Okay, it's almost not full rank. It's very close to being not full rank. And when I try to do an inverse, it's very unstable. And it's done something to make it more stable, to try and automatically make it more stable. That is kind of adding a regularization term. What it does is it adds a small factor before it does this, and that will add a regularization term which will prevent the curve from moving too quickly. Effectively is what will actually happen here. You can, I don't remember how to do this now. You can force it to fit the data exactly, and then it will actually go through all the points. But right, so this is 50. Okay, if I go 50, yeah, if I do 50, it's still not quite hitting this guy, but it did manage to go through both of these points, right? But it's now doing something very well. Right. All right, so I've now given you a very powerful and a very dangerous algorithm to go and work with. You can say, I want my residuals as small as possible. Let me crank that degree up to 50. Look how, I can go and calculate the residuals. I should be able to get smaller and smaller residuals the higher I make this degree. I'm closer and closer to all my data points. All right. So what was the right degree to use here? You think 50 is good? This one, I basically went through all of them.
I agree with that. Back once we started getting
yeah, so you think about 15? All right, who thinks about 15 is about the right number? Who thinks should be something else? I think we could go. Yeah, so you think 5 did a better job, right? 5 is kind of splitting the difference between these things, but our original model was that we were observing the data from a true curve with some normal noise on each of these data points. So maybe we should expect to see some deviation here from the true curve. So maybe this is better, but how do we quantify that, right? How do we figure out how to do that? Well, this will be what we talk about in the next lecture. Okay, we'll talk about this kind of this danger where you can fit stuff better and better, but maybe this is not good, and how to deal with this. We'll talk about so the idea of cross-validation, which is probably the most important tool in data analysis from the last like 50 years. Okay, so that will help us kind of solve this issue. All right, we'll do that, and remember, quiz 3 will now be on Monday. And if you're going far home at a car, please be careful out there. Hopefully, most of you can walk.